right. Do we have more people in here yesterday?
Yeah.
Wow. Is that something I said?
I think in your video, I think you said if people don't show up, you'll do attendance.
Yeah, that's an excuse to show up. All right. So first thing, I've been asked to read the following announcement regarding looking for a note taker. So a student in this class has a documented disability that impacts his or her ability to take comprehensive lecture notes. The Disability Support Services Office is requesting that someone, preferably two of you, volunteer to share your notes. You do not have to do anything different than you would for yourself unless you choose to. The DSS office will provide you with NCR paper, which is a carbonless 2-part 3-hole punch-lined notebook paper, which basically means you can take your notes on this paper and there's a copy of it made automatically. However, some people are taking notes electronically, and the student has expressed a preference. If you're taking electronic notes and you're willing to email a copy to them, that would be the ideal. If not, then using the NCR paper would be a second option. So is there anybody who would be willing to volunteer his or her notes? Cool. Anybody else? All right. So, cool. So thank you. So come up and talk to me after class if you want, and I'll give you the email address and introduce you. Okay, cool. Thank you. All right. So I wanted to talk a little bit about the 222 final. Yes?
I tried looking at the Java reference source, but it took me to the Oracle site. Where exactly is the reference?
Let's see. These things change over time, so. And I think on the left there's a section for different languages, and you just want to follow with the one for English. But let's double check. So Java documentation. And core API is English, so you can just do English 8. Well, let's try that, and let's try the programming guide. So I think this is the one I was thinking of. And we don't necessarily know how to use this yet, but different classes, which we're going to talk about today, are located over here. But as you can tell, there are a few classes in here, and it's a little bit tricky to search through all of those. So here's what I actually do. If I want to know about the scanner class, I just say Java scanner class, and chances are the first or second thing that comes up is from oracle.com, and that takes you to the particular page that has all the good stuff in it. But if you were over here and you searched for scanner, you would find it down here, and that'll take you to the same page. But there's just so many things over here to look for. So Java, name of the class, and then the word class seems to get you there most of the time. Yeah?
I tried to get the hello world based on the notes I took yesterday. And when you did the public static main void, you just typed in strings, right? Or string?
String, bracket, bracket,
okay.
Variable.
Okay, because I missed that part, and I was wondering
okay.
if you had an alias or it wouldn't take good things.
Okay, and I neglected to post the hello world, but I posted posted the code from this morning's class, which was a rectangle thing, and that's got a main program in it that you can pull up, and we'll do some code today, and I'll post that up also. But yeah, there's a good prototype.
Yeah, I fooled around with it and then just put that in on my own and got it.
Oh, cool. Okay, awesome.
I started looking at tutorials point because I couldn't find a doc.
Yeah, tutorials point is good. And I still have Java books in my office if anybody wants a hard copy. A few people took me up on it. All right, any other questions so far? All right, so let me make a few comments on the 222 final. And these are just some things that I tended to see again and again while I was grading, and so I made some notes to myself and told myself I was going to talk about a few things. And most of it had to do with recursion. There was also one thing with dynamic programming, but most of this is about recursion. And there were 2 exams, so they weren't exactly the same questions. So this one, you were counting the number of nodes in a tree. The other question was counting the number of nodes in a list. So let's look at this question. So we want a function named count that tells the number of nodes in a tree. And the algorithm is if the root's null, return 0, because there's nothing in the tree. Otherwise, count the number of things in the left and right subtree, and then add 1 for the root. So here's the pseudocode that we're thinking of. So count of tree. So here's our tree, and it's got some stuff. And so on. And what's the basic strategy of recursion? Someone hires me to count nodes in a tree. Okay, they're paying me really well, so I accept this job. Give me any tree, I'll tell you how many nodes there are. Okay, so someone hands me a tree, says, tell me how many nodes there are. So I do the following. I say, well, here's 1. And I take this tree and I hand it to a friend. I subcontract and I say, hey, can you count how many nodes are in this tree? And they say, that's got 5 nodes. I say, thanks. How many nodes in this tree? Well, that's got 100. Okay, thanks. 100 plus 5 plus 1, that's 106. And that's the answer I give to the person who asked me. That's recursion. Okay, so I'm counting the root node, that's 1. I'm asking my friend, that's the recursive call to myself, to count the number of nodes over here and the number of nodes over here, and I just add them all up. So I want to count tree left. I want to count tree right. Add those up, add 1 and return that. Anytime that you do recursion, you've always got 2 things to worry about, and they're usually the same thing. The first thing to worry about is how does this recursion end? Because if every time I come into count, I'm going to call count again, I've got an infinite recursion, and I'll blow up my stack. So there's got to be some situation in which I come into this function and I don't recurse.
Root is null.
Yes. And that's the other possible problem is any time that you use something like tree arrow left, tree could be null, that's going to be a seg fault. And those are the same situations. So this is the edge case, this is the base case. If tree is null, return 0. And that's right in the problem definition. The first thing it says, if the root is null, return 0. Otherwise, we want to count up these things, right, and return 1. And I saw a lot of code on all of the recursive problems where, you know, I saw a call to count where you pass tree arrow left, but there was nothing being done with the return value from that. So this is saying, okay, take this tree, hand it to a friend, and say, please count the number of nodes. And then you turn away and you take this tree, hand it to somebody else, and say, please count the number of nodes. And you never listen to what they tell you. They counted them, but you haven't done anything with that information, right? So you actually want to make sure that you do 1 plus this plus that, right? That's what you want to return. And all the recursion problems, I saw cases where people called the function successfully but didn't use the return result. And that's a really easy thing to do accidentally, right? But if you work through the solution that you've written down to confirm that it's actually solving the problem, it should jump out at you at some point that, hey, I'm not actually like, you know, what am I returning? I'm returning 1. Or I don't have a return statement at all. So, so just calling count doesn't somehow adjust some internal variable that you're going to return magically, right? You've got to do a bit of the work yourself. On the other hand, there is a certain magic to recursion. which is when I write this function count, think about your one-sentence description of this function. What does count do? Count accepts a pointer to a tree and returns the number of nodes. This can be any tree, including a null tree. Right? If it's a tree that has no nodes, doesn't even have a root, this will still work. It will return a 0 in that case. Once you believe that internally, you should be totally comfortable writing this, even if tree arrow left happens to be null. If it's null, you're not going to blow up. It's just going to say, oh, that's null. It's going to return a 0. But most of the code I saw actually said if tree arrow left is not equal to null, then call count and save that in some variable. Otherwise, set the variable equal to 0. And then same thing on right and so on. Right? It doesn't do anything wrong to do that, but it's extra work and it's extra writing. Because the way you wrote your function with this up here, tree can be null. That's fine. Now, we can't say null arrow left, right? But if tree is not null, tree arrow left is something, and we can just pass that to count. And we know we're going to get back a valid count, which might be 0, but that's fine.
So,
Yeah?
so basically that is the high of tree,
It's a what?
the high of the tree file.
Yes. So we're
I completely right. Is the high of tree or I saw it look like the high tree BA4.
high tree.
The high of tree is
Oh, height.
yeah.
This is similar to height, yes. Height,
Right node.
yeah, so with height, we're basically finding the height of the left and right subtree, and then using the maximum, adding 1. Here, we're just counting nodes, but it's the same idea. We're doing our operation on the left and right subtree, taking the results of those, and using that to get the answer to our original tree. Yeah, exactly the same process. All right, so same thing here with tree traversal. So this was a 3-way tree. Other section got a 4-way tree. So tree with a left, mid, and a right. And the definition of traversal is inherently recursive. To traverse a tree in left, middle, right node order means traverse the left subtree in that order, traverse the middle subtree in that order, traverse the right subtree in that order, and then print out the root data. So traverse tree. Traverse the left, traverse the middle, traverse the right, and then print the root node. And you need the base case so you don't recurse forever, and it's exactly the same base case. If tree equals null, then we don't have to do anything, just return. And as long as we have that base case here, we don't need to say if tree left is not null, then traverse tree left. We can just traverse tree left, and if it's null, it's going to be a no-op. It's just going to return. And like I say, it's not that having those if statements causes any problem. It's a minor slowdown. It's a little bit more code. But I want to make sure that you think about the idea that, oh, I could pass a null argument here, and that'll work, because when I wrote my traverse function, I wrote it explicitly, so you could pass a null tree and it will do the right thing. So take advantage of that. Let the recursion do the work for you as much as possible. Okay, let's talk about happy trees. So this was a pure recursion exercise, right? 3-way tree, same tree we just had, is happy if either the tree is empty, right, it has no nodes, or exactly one of its 3 subtrees is happy. So,
Cool.
yeah, the other one was a cool tree. So happy tree, and what did we return, a 1 or a 0? Oh, we returned H or S, okay. So this returns a character. Tree is a node pointer. So got to take care of the null case, and that's actually specified for us. If the tree is empty, it's happy. So if tree is null, return happy. Otherwise, what do we want to do? We want to see if exactly one of its 3 subtrees is happy. Well, we can do that easily because we have a function that tells us if something is happy. It's called happy. So we can say something like left equals happy, tree left. Mid equals happy, tree mid. Right, and these are characters. All right, so how do we know if the tree is happy? Well, if left is equal to H and mid is equal to S and right is equal to S, then exactly one subtree was happy. Or if left is S and mid is H and right is S, then one subtree was happy. Or left is S and mid is S and right is H, then one subtree is happy. So if blah or blah or blah, we can return H. Otherwise, we can return S for sad. That's the most direct representation of that, probably, if exactly one of its subtrees is happy, because we wrote an if statement for each possible case. There's other things you can do. So we could make a variable that's equal to 1 if this is happy and 0 if it's sad. Right? So we could do something like integer left equals happy equals C, sorry, H. And this is a shorthand way of saying if happy is equal to H, set left equal to 1, otherwise set left equal to 0. And now we have 3 integers, left, mid, right, 1 if the subtree is happy, 0 if it's not, and we want to know if exactly one of those is equal to 1. And what's the easiest way to tell if exactly one of 3 integers is equal to 1 without a bunch of if statements? A bunch of people did this.
Some?
Yeah, add them up. If they add up to 1, then exactly one of them was 1 and the others were 0. So if left plus mid plus right is equal to 1, it's happy, otherwise it's sad. Lots of different ways you can do it. But again, I saw things like, calls to this and then return something, I don't know what. But calling this without using the return value doesn't get you any benefit. And here, if you start putting in, if tree left is not equal to null, then see if the tree left is happy, and so on, that starts getting more complex. And I got, full page versions of this in a lot of cases where it kind of felt like you knew what you were trying to do, but the recursion was just tripping things up, right? So it helps with recursion if you can sort of up front decide what this function is going to do before you write it, right? And you can just kind of dream. I would like a function that does this, right? Well, you're the programmer, so you can define this however you want and then see if you can actually write a function that does that. And maybe your dream was too ambitious and it has to do something simpler, and then you have to do some work with the result of that. But chances are, if you just say, I want this to take a tree and tell me if it's happy, I don't care if the tree is null or not, I want it to do the right thing, right? And then work from the definition, and chances are it comes out fairly rarefied, but not always. Okay, and then question 4 was the one I said was going to be more challenging, so it was either deleting every other node or duplicating a list with new nodes in memory. And despite being, a more challenging problem, I didn't see anything in there that gave me grave concern. You could do this recursively, and it turned out to be really easy. And honestly, when I wrote this problem up, I didn't think about the recursive approach. And a few people did it recursively, and it was like a few lines of code, and that was really cool. But I was thinking of it as an iterative exercise, and it's mostly an exercise in housekeeping, keeping track of what's pointing to what and so on. But people did a good job on this pretty much across the board, so that was fine. AVL tree was what it was. Heap and heapifying and inserting and deleting was fine. Let me talk about dynamic programming. So using a memory cache to speed up a recursive function. And here's something that we put on the board before the exam. So here's a function that takes some argument n, and there's some section of expensive recursion. This is where it's calling itself multiple times probably and solving subcases, and this is the stuff that takes all the time. And then at some point there's, you know, some return of something. That's probably could be part of the expensive recursion. So here's the non cached version of a recursive function. It's just got a bunch of stuff it does in a return statement, and that's what this cool function was, right? So a couple of return statements, but same basic structure, right? So you want to speed this up using memory cache. You do the following three things. One, you create an array of save values, right? So this function always returns integers. Your integers are always positive. If you look at this, the smallest it can be is 5, and it just gets bigger after that. And it always takes a number between 0 and 50. So I could make an array of 51 ints, right? Call it save or something like that. So in the beginning of your function, see if element n in your save array is valid, meaning that it actually stores the value of function n. So either use a flag or use the fact that this should always be positive, and so set it to 0 if it's not valid and positive is, but somehow determine if it's valid, and if it is, just return it. And you're done. One line of code, no recursion involved. If it's not valid, you got to do some work. So do your expensive recursion, and at the end of your recursion, instead of returning blah, get rid of that line and do one other thing. Save bracket n equals blah, and then return save bracket n. So you can take a function and simply add something in the beginning, add something at the end, and now you've got dynamic memory in use. You've got caching of results, and this will speed it up. And if you do that to this, right, you have an extra statement in the beginning, you have some initialization outside. Your return statement, says blah equals all of that, and then save blah in your array and return blah. And so it's a few extra lines on here. But a lot of people got into all kinds of things where they check to see if save haha -1 was valid, and they check to see if save haha -3 was valid. And if it was valid or not valid, they did the appropriate thing to either call this function or read from that, and so on. Let the recursion work for you, right? Think about what this function is doing. It takes the value haha, it returns cool of that value, and it does it efficiently using memory caching. If that's your mindset of what this function does, I can happily just call cool haha -1 and believe that it's going to solve this efficiently, because it's going to look in the array, and if it finds it, it's going to return it, and if not, it's going to save it before it exits, and it'll be saved for the next time that I use this. And so I'm good with simply putting in a check in the very beginning and putting in a save at the very end. So again, it's not wrong if you do it the other way, but it's more work. In some cases, it's a lot less efficient because people were, depending on where you do your caching and your checking. But mostly I want to make sure that you think about why doing this is sufficient, right? Belief in recursion. So I think those were the main things. There was an insertion sort, there was a selection sort. Everybody got a quick sort. You got different words in the try. Everybody did really well on the try. That was awesome. Because I've taught tries every time I do 222 and they never take, and pretty much everybody seems to know how tries work now, so that was really cool.
Tries should be kind of simple to understand.
Yeah, I guess brain surgery is too if you go to med school, but I know tries were really funky to me when I first learned them, but you know, when you work through them, then it made sense. I did not mean for the hash question to be arithmetically challenging, and it was, and I kind of apologize for that. I probably need to do something different in 215 in the future. Let's quick review of modulos, right? So number modulo divisor. This means take your number, divide it by the divisor, and find the remainder. Okay, what's a remainder? It means put your divisor into your number as many times as you can without going over, and then see what's left over. Okay, so 23% 5 means take 23 divided by 5. Well, 5 will go in exactly 4 times, and your remainder that's left over is 3. So that's what 23 mod 5 is. It's 3. It's the thing that's left over. Okay, so here's one tricky part. If we do 5 modulo 23, that says take 5 divided by 23. How many times does 23 squeeze into 5? 0. And how much is left over if we take 23 times 0? And we got a remainder of 5. And anytime you do something modulo something bigger, you just get that first number. That's what it's congruent to, because the bigger thing goes in 0 times. So that's one thing to keep in mind. The other thing is, if we do modulo 10, so here's 472,362 mod 10. Take 472,362 and divide it by 10. And we know that's going to be 47,236 because we just ignore that. And the remainder is going to be 2. That's just that last digit. So modulo 10 is just saying give me the last digit of the decimal expansion. If we did modulo 100, it would be 62, the last 2 digits. So modulo powers of 10 should be pretty quick to do. And again, if I just had, 6 modulo 10, that's 6 divided by 10, that's 0 with a remainder of 6. It's still just the last digit, even though there's only one digit. So on the hash question, the idea was once you figure out the value of this last key plus probe squared to reduce mod 10, you just take the last digit. But that tripped up more than a few people, which I didn't intend, but that's what's going on with mods. All right, so I still have your exams in my office. If you want to come by and look at them or ask for details on any of these questions or questions I didn't go over, you're welcome to do that. But people do
I'd honestly
well.
like to look for myself to see if I actually did ace my exam.
Oh yeah, yeah, you can look at it. All right, good. All right, let's make sure I'm not skipping anything.
What did you remove in work?
Say what?
What did you remove in work?
Everything.
It wasn't important, right?
Better not be. No, it's stuff I did from the last section, so we'll do stuff our own way. Let's go back to our hello world.
What happens when you compile multiple programs?
You get multiple class files,
Okay.
which we will do shortly. All right, so here's a hello world we were playing with yesterday, right? Just a standard public static void main, and then just our one print line which prints out hello. So compile it with Java C, and then run it with Java and the name of the class hello, and it says hello. All right, so I want to look at these arguments. I want to print out the value of element 0. Args is an array of strings. So args bracket 0 is element 0. That's the first element in the array. It's the first string. So let's print out the value of args bracket 0. And let's print out args bracket 1 and args bracket 2. And if I say Java hello, guess what? I get an exception. It doesn't say segfault, but it says java.language.array index out of bounds exception. How's that for an error message? And it even tells me the index that was out of bounds was a 0, and this happened at line 5 in the file hello.java. So that's pretty specific information. I can come down here to line 5. That's where I went wrong. It says I was trying to index element 0, and that was out of bounds. There is no element 0 in my args array. Currently my args array has nothing in it. Well, that makes sense because it sounds like args should be the arguments that I used when I ran this program. So let's try this. Java hello, this is a test. Arg0 is this, args1 is args2 is a. So this is how we access command line arguments. We just take them as the elements of this string array, and it's a bit less painful than char star star argv, etc. All right, so that's on the shared area. All right, so let's talk about objects and classes. So I'm going to make something called main. So there's an empty main program, does nothing. When you use an IDE, by the way, like IntelliJ or Eclipse or something, you can check a little checkbox and it'll write all of that for you, because it's always public static void main string bracket bracket args. So you don't have to type it endlessly, but you do for now because you're not using an IDE. So there's an empty main program. Okay, so there's a couple of terms that we're going to toss around. There's the term class. And when we define something like, you know, my main or hello world, we started off by saying class space hello world. Okay, this is kind of like a struct in C. When we say struct node curly bracket integer data semicolon struct node star next semicolon close curly bracket semicolon, right? We're defining what this structure looks like. What are the pieces of it? Okay, a class is a description of one of these superstructures. It describes what the pieces of it are. Okay, but in this sense, it's kind of like a blueprint or a recipe. It's a description of something, but it's not the actual something, right? A recipe for cookies is not something you can eat. It's a description of how you make a cookie. Okay? If you actually want to create an instance of this class, that's what we call an object. And that's what you get, for example, when you say malloc in C, when you actually allocate memory, right, and point to it. Or if you like, it's the actual cookie. So the class is the description of how you make something. The object is the thing that you've actually made. And I'll do my best to be extremely consistent with those terms, because they're fundamentally different concepts, right? Class is a description, and we write class descriptions all the time in Java. But then sometimes we say, I want this variable I to be an instance of this class. I want you to construct an object of this class, right? So this is an instance of a class. And creating this is sometimes called construction, it's sometimes called instantiation. So let's see how this works. And it gets a little weird because our main program always goes inside a class, right? And the class could be called anything that we want. The main program is always called public static void main. But it sits inside a class because everything in Java is done through classes. And when you run a program, you say Java space class file name, right? The Java virtual machine will go inside that class, right? And it will look for a function called main, basically. It's a little more subtle than that. But let's not worry about the main class. Let's go ahead and make our own class and treat this like a struct. So let's make a rectangle class. So class is a keyword. It says I'm starting the definition of a class. It's like struct in C, okay? So I'm defining a class called rectangle, curly bracket. Everything I put in here is part of the class. Okay, so what does a rectangle have? Well, it has, let's say, an integer height, and it's got an integer width, and I don't know, does it need anything else? Let's give it a color. I don't know why. That could be my whole class. Okay, it's a new type of variable. It's not an integer, it's not a string, it's a rectangle. And it has these three pieces to it.
It could be a highway warning sign.
Could be a highway warning sign. Okay, so I've got my main program and I've got my rectangle. So if I say compile rectangle, I get a rectangle.class. That's the bytecode corresponding to this class. I can't run my main program because I haven't made a main.class. And I can't run my rectangle because if I do, it will say I didn't find a public static void main string bracket bracket args. Right? Please define the main method as. So my main has a main method in there. So let's make some rectangles. So I'll make a rectangle called R1. I'll make a rectangle called R2.
You don't need to include rectangle as part of your...
I don't, because it's in the same directory I'm in. If it was in a different directory, then you got to do things when you try to run, basically paths. Okay, so let's look at R1's length. R1's a rectangle. I'm not going to do anything with R2. I'm just going to print out R1's length. So I'm using the plus sign to say I want to concatenate these things together in the output. So I'm going to print out R1's length equals, and then I'm going to print out R1.length. And I'm using this period like we use it in structures in C. There's no arrows. When I say rect R1, R1 is kind of like a pointer to a rectangle. It's a reference to a rectangle, basically. So I just use a period, right? There's no arrows, there's no star up here, but it's cognizant of the fact that we always really want a pointer or a reference to a rectangle. So I'll just print out R1.length. That should give me the length of the rectangle. Now when I try to compile it, it's going to notice that R1 has not been initialized. Oh, that's different. What did I call it? I called it width. Okay, I'll call it length. Okay, so now, if I compile my main program, it'll say R1 might not have been initialized. Right, and down at line 6, in fact, I'm using R1.length, and I never gave R1 a value. So this is kind of saving you from those null pointer exceptions, from those seg faults in C, where you said this is a pointer to a node, but you never called malloc. And then when you tried to dereference part of that variable, you were dereferencing null, and you get a seg fault. So it won't even compile. Right? Now I could give this thing a value. And that'll compile fine.
Oh dear.
And now when I try to run it, it'll say null pointer exception. That's a seg fault, basically. But remember, this is running in a virtual machine, so it understands what's going on. It understands I was at line 6, and I tried to access something off of null. Okay, so how do we do this? We need to do something like a malloc. So instead of malloc, we have a keyword called new. We just say rectangle R1 equals new rectangle, parentheses, and a semicolon. And you can do it on one line like that, or you could do on 2 lines. The first one is integer I equals 0. The second one is integer j, semicolon, j equals 0. Same idea. So those actually construct rectangles. So let's compile that up, and let's run it, and it tells me the length is 0. So fields default to 0 if you don't specify them, integer fields.
That's kind of useful.
That's kind of useful, as long as you don't go back to C and forget. So let's change this. Let's make this thing default a rectangle to, I don't know, 7 by 5. So now when I construct a rectangle, its length should be 5, its height should be 7. Around this time, you should be getting fairly annoyed that you have to keep saying java c rec.java, java c, right? So let's set up an alias. Alias c equals quote java c star.java. C for compile, and alias r for run equals java main. So now I can say C to compile, and I can say R to run, and it tells me R1's length is 5. And I just used a little bit of 224 knowledge, and my mood just went up a bit. Because now I get to worry about the Java code, not about did I say Java C, or trying to use the up arrow to find the last compile command and all that stuff. Right? Is that a big deal? No. But it takes almost nothing to do this. And if I'm going to be working in this area a lot, you know what I might do? I might make a file called setup, and I might put this stuff in there. And when I come in here, I'll just say source setup, and it'll execute those 2 alias commands, and now I'm good until the next time I log out. And now I have my shortcuts. All right, so just little Unix customizations there.
Does that only work with one program, or can the alias be applied to multiple programs?
So alias is just a substitution. It's just saying when I say C, type this in. In this case, I said java c star.java, so that compiles everything in my current directory. Okay, now I'm not planning to have 100 Java files in here. I'm going to have 2. If I change main and I say C, it's going to recompile rect also. That doesn't bother me. But if I had 100 files in here and they were long and I didn't want to recompile everything, what would I do? Makefile. Yeah. So there's where makefiles can help you. And usually what I do is I make a little script called C, so I can just say C space rect and it'll add on the .java for me. And stuff like that. But you know, it's your environment. You can set it up however you like. Right? That's the fun of Unix. Okay, so let's play with this a little more. We got a few minutes. So R1's length is equal to whatever it is. It defaults to 5. Let's go ahead and change it. Let's set its length equal to 100. And then let's print out the length again. And no big surprise, right? Next time we print it out, the length is 100. And this mostly looks like C, right? This is you know, a C statement if R1 is a structure and length is a field in it. This is a malloc, right? This is a printf. So syntax differences, but basically the same idea. Now, when we talk about data structures, we talk about the interface between a user and a data structure. And for example, when we build a queue, your queue might be implemented with a linked list, where you insert at the first node and you remove from the last node, or maybe you insert at the last node and you remove from the first node, or maybe you have a circular array with a pair of pointers and you use this pointer for insert and this pointer for remove, and maybe you increment or maybe you decrement, and so on and so forth. And when we create a data structure like that, we can hand it to the user and say, you know, you can call insert and remove and is full and is empty. But if the user decides to come in and say, you know, is q arrow next equal to null, they're tinkering with the internals of our implementation. They're not treating this as an abstract queue. They're saying, oh, I know how you did this. You used a linked list, and I don't want to call your function because I want to know if the next thing is the last. So I'll say is q next equal to null. And next week I change this to use a circular array, and their code breaks. So sometimes what you want to do is you want to hide information from the user. So I can say these things are private. And if somebody tries to look at these directly or tries to change these, I don't want them to be able to. So now if I try to compile this, the compiler will say, hey, in main.java, you're trying to access the length field of a rect. That's private. You're not allowed to do that. And it'll refuse to compile this. And that's really useful for making nice, clean interfaces. It's something we call information hiding. It's saying, I don't want you to touch the stack pointer because you don't understand whether I'm incrementing it or decrementing it before or after inserting or removing, right? I understand that because I wrote the code, but I don't want you to tinker with that. And so you can actually hide pieces of your code from the outside world. But we still want the user to be able to set the length of a rectangle or to read what the length of a rectangle is, right? So we're going to create what are called accessors and mutators. And this will be a very controlled way to still give the user access to the information we want them to have access to, but strictly on our terms. And this is part of encapsulation and information hiding. Okay, so we'll start from there tomorrow.